This is magnesium ribbon. When the ribbon is put to flame, it reacts with oxygen in the air and forms this white solid called magnesium oxide. This is an example of what we call an ionic compound. In this video, we'll discuss how ions bond together to form ionic compounds. So let's get started. Before we talk about how to put these ions together and how we make ionic compounds and we name those ionic compounds, let's talk first about a little review, okay? All right. So what's an ion? We said before that an ion is an atom or a group of atoms that has an electric charge. It could be a positive charge or a negative charge. The charge of an ion depends on whether it has gained or lost electrons. So since electrons are negatively charged, an ion that has lost electrons will have a net positive charge, and we call these cations. We'll look at that. Okay, so far so good. An ion that gains electrons will have a net negative charge. We call those anions. So what's the point? Why are these atoms even exchanging electrons in the first place? Here's how it works. Once again, every atom or every type of element really wants to have a full set of outer electrons, valence electrons. And that's 8 valence electrons. An atom feels most stable that way. But there's only one group of elements that has a full set of electrons, and that is the noble gases. So the other elements aren't quite so lucky. They do the next best thing. They either give away or they take electrons in order to create that stability to feel like a noble gas. And as it happens, we said that we can tell exactly what kind of ion a parent atom will form based on its location on the periodic table. And by parent atom, I mean what was the atom before it turned into an ion. That's all. For example, we see that metals tend to lose electrons in order to become more stable. A good example of this is sodium. Sodium is a metal that only has one valence electron. I highlighted it in blue on this slide. However, underneath that outer shell with the one valence electron, you can see an energy level with a full set of 8 valence electrons. So instead of trying to gain 7 electrons, sodium will simply give away that one valence electron. There it goes. And that leaves it with that energy level with 8 valence electrons. And that gives sodium much more stability, the stability that it very much desires. Since sodium loses an electron, to do this, it now has a net charge that's positive. So we designate it like this. We simply put the symbol for sodium with a charge of 1 positive unit. By the way, whenever we have just one positive or negative unit, we don't show the number 1, we just show the positive or negative symbol. That's it. So, since these metal atoms tend to lose electrons in order to achieve a stable configuration, that means they become positive ions. You're losing negativity, right? Again, we call these positive ions cations. Now, non-metallic atoms, the one that are over here on the right of the periodic table, they tend to gain electrons in order to get that stable configuration. For example, we have chlorine that has 7 valence electrons. You can see them there on the diagram. To have a full outer set, chlorine needs to take 1 more electron from, say, a metal like sodium. It will then have a more stable configuration of 8 electrons in its outer shell. Since chlorine gains an electron, like so, it now has a net charge of 1 negative unit, or -1. We designate it like this. We show the symbol for chlorine with the negative symbol. And remember that nonmetal atoms tend to gain electrons in order to achieve that stable configuration. So they become negative ions. We call these anions. So let's do a quick little review here. How about magnesium? What will magnesium become? Will it become a positively charged ion or a negatively charged ion? How about it? Yes, magnesium will be a positively charged ion. Magnesium is on the left side of the periodic table. It's one of the metals, and so therefore it will lose electrons and be a positive cation. One more, how about this one? How about sulfur? Yes, sulfur is a nonmetal, therefore it's going to gain electrons, and it will become a negatively charged ion. And let's quickly recall that we can know what kind of ion is produced based on where that parent atom is on the periodic table. For group 1 elements, we know that they lose one electron and form +1 ions. For group 2 elements, we see that they lose 2 electrons, they're 2 valence electrons, and so they form +2 ions. For group 13 elements, they lose their 3 valence electrons and form ions that have a +3 charge. So with the exception of boron, those were all metals. Let's talk about nonmetals now. Starting in group 15, we see that these are now going to gain electrons. Elements in group 15 will gain 3 electrons. That means they take on a charge of 3 negative, or -3. Group 16 nonmetals will take on 2 electrons, giving them charges of -2. And group 17 nonmetals will take on 1 electron, giving them a charge of -1. So now we're all set. Let's talk about how these ions will come together and form compounds. So those electrically charged ions don't just hang out by themselves. If you have particles that have opposite charges, those particles are going to be attracted to each other. So when 2 or more of these charged particles combine, we have an ionic compound. That's what we call it, an ionic compound. So for now, we're only going to talk about what we call binary ionic compounds. All we mean by that is we're only using 2 types of elements. So here's sodium, for example, and here's chlorine, both of which are now ions. All we need is 1 sodium to combine with 1 chloride, and those come together to form sodium chloride. By the way, when we show the charges on those ions, we write them as superscripts. You can remember Superman flies overhead, right? So superscripts are up above the symbol. In this case, we have 1 positive charge on sodium and 1 negative charge on chlorine. Whenever we have 1 of either, we don't write the number 1. It's just what we call understood. We simply write the positive sign or the negative sign. Now, if we have 2 or more charges on an ion, like we see here for magnesium and the nitride ion, then we will actually write the number for those. Here we have magnesium with 2 positive charges and a nitride with 3 negative charges. Or we can just say magnesium with a +2 charge and the nitride with a -3 charge. So let's go back to sodium and chloride again to show you a principle here. And that is that when ions come together, they must come together in the right proportions so that the overall charge of the compound will be 0. In this case, all we need is 1 sodium and 1 chloride, and those 2 can come together to give us sodium chloride. It's really easy in this case. So they just combine in a 1-to-1 ratio. Now, the same can be said for calcium and oxide. The calcium ion is a +2 ion, and the oxide ion is a -2 ion. They will come together in a 1-to-1 ratio as well, because their charges are equal in magnitude. You see that? Equal in magnitude, but opposite in charge. So, simply a 1-to-1 ratio, and they come together to give us calcium oxide. And by the way, the same could be said for putting something like aluminum with a +3 ion and nitride with a -3 ion. Putting those together would still be in a 1-to-1 ratio because the charges will cancel each other out and you'll have aluminum nitride. Starting to get it? But what if the magnitudes of the charges aren't equal? Now it requires us to balance the amount of cations and anions we have so that those overall charges balance each other out and giving us a net 0 charge overall. For instance, if we have magnesium with a +2 charge and each chloride has a -1 charge, then we're going to need to have 2 chloride ions to balance out the +2 magnesium ion. And that will give us magnesium chloride. Notice that in the formula for the compound, we have 1 magnesium and 2 chloride ions. Again, if there's just 1 of something, we don't actually write the number 1, it's just understood. If you see magnesium there, you know that there's at least 1 of them there. We do have 2, though, of the chlorides. You're probably asking, though, is there a simpler way of doing this? And there is. I like to call this method swapping and dropping, or just swap and drop. So here we go. Let's use the aluminum ion and the oxide ion as an example. Aluminum is a metal cation. It belongs in group 13 and has a +3 charge. You see that? +3. Oxide is a nonmetal anion. It belongs to group 16 and it has a -2 charge. You see that? So if we take the numbers, just the numbers, not the signs, if we take the numbers that are in the superscript position and we swap them and move them into the subscript position. You see that? You see what I'm doing there? So the 2 is going to go down here and the 3 is going to go down here. When we do that, we actually come up with the correct answer, the correct combination. Aluminum oxide, in this case, has Al2O3. And this gives us the proper proportions for each ion in our compound. And by the way, if you want to know how many total electrons were transferred in this transaction, all you have to do is look at the compound, multiply the subscripts together, and that will give you your total transferred electrons. Now take a careful look at the way that we write the compound. For the ion, we write the charge in the superscript position up here, up top. You see that? But notice in the compound, when we want to indicate how many of each ion is in that compound, we put that number in the low position. We call this a subscript, sub like a submarine. So again, in a compound, when we're writing the compound, to tell how many of each type we have, we write a subscript. You see that? So charge is a superscript. Amount in the compound is a subscript. Okay? All right. Let's try it now with the potassium ion and the phosphide ion. Potassium is a metal cation. It belongs in group 1, so therefore it has a +1 charge. Again, the number 1's understood, but I tell you what I'm going to do. I'm going to go ahead and put a 1 there. You like that? So that we'll know what's going on. The phosphide belongs in group 15 and it has a -3 charge. So here are our numbers again. We're going to take those numbers, we're going to swap them and drop them. Okay? So now we're going to end up with what? K3P1. Except we don't write the number 1, we just leave it as P. So here we go, K3P. We call this potassium phosphide. All right, here's one for you. We have lithium with a +1 charge. It's from group 1. And sulfide. It's in group 16 and it has a -2 charge. What kind of compound will this make? See if you can swap and drop and figure it out. All right, hopefully you said Li2S. We see that we have a 1 here, understood, and a 2 here. So we'll take the 2, swap it and drop it, put it right here, just like we did here. And the 1 we'll swap and drop here. And we just understand that there's a 1 there. All right, let's try another one. How about this? We have aluminum with a +3 charge. It's in group 13. And chloride has a -1 charge. Again, the 1 is understood. So what do we have here? Did you say AlCl3? Hopefully you did. We have the 3 that swaps and goes over here, and the 1 that goes over here. So we have Al1, understood, Cl3. One quick note, you don't have to use swap and drop if your charges are equal but opposite, like for sodium and chloride. Those just go together in a 1-to-1 ratio to give you sodium chloride, or calcium and oxide. Notice that you have equal but opposite charges. You don't have to use swap and drop. They just go together as a 1-to-1 ratio to give you calcium oxide. Okay? So only use swap and drop if you have different magnitudes of charges. So now, how do we name it? Let's give this a name. The first thing to remember in writing binary ionic compounds, in other words, compounds that have only 2 types of elements, is that the metal or cation is named first. So the cation, the metal is named first. And by the way, the name of that element is not changed. We'll just call it magnesium or sodium or calcium or what have you. After the metal, the nonmetal is named second, or the anion is named second. And when we have a binary ionic compound like these, the ending of that nonmetal name is changed just a little bit. And you might have heard me say this along the way. We change the ending of the name to IDE. So instead of saying chlorine, we say chloride. Or instead of oxygen, we say oxide. Or instead of nitrogen, nitride. Again, this is for whenever we have a binary ionic compound, where only two elements are involved in that compound. So for a few examples, NaCl is simply sodium chloride. Mg3N2, notice again there's only two types of elements involved. Even though there's more than one of each one, there's only two types. This is still a binary compound. This is magnesium nitride. Okay? And then here's another one. Aluminum, doesn't change the name, sulfide. Okay? Sulfur is changed to sulfide. So there you go. That's how you name these binary ionic compounds. All right, it's time to practice from start to finish now. Let's say we have calcium and fluorine. What compound will they form? We start by locating calcium. We find that it's a metal. It's in group 2, which means it's going to have a +2 charge, right? Okay, so there's our +2 charge on our calcium ion. Next, we have to find fluorine. We find that fluorine is a nonmetal. It's in group 17. So therefore, it's going to have what kind of charge? The -1 charge, right. So there's our fluorine with our -1 charge. Now let's just use our swap and drop method. I'm going to put a 1 there for fluorine, just so we know what's going on. So how many calciums will there be in our compound? That's right, we'll have 1 calcium and then 2 fluorines, right? Swapping and dropping. So we get calcium fluoride, CaF2. And there's the name of it for us, calcium fluoride. Charges go up top, they're superscripts. But how many we have in the compound, in the finished compound, those go down low. Those are subscripts, okay? Okay, here's your assignment, guys. I've got 2 combinations here. One's beryllium and phosphorus, and then this one is potassium and oxygen. 2 compounds, one between beryllium and phosphorus, and the other between potassium and oxygen. Tell me the formula and the name of each one. Got it? You can simply submit your answers on the LMS. All right, guys, thanks for hanging in there with me. Today we talked about how to put these ions together to form ionic compounds, and how we have to use proper proportions of our ions when putting them together so that the charges cancel out. We then showed how we can use the swap and drop method for situations in which the charges on our ions are different in magnitude. And finally, we introduced information on how to name these binary ionic compounds. As always, I hope this has been helpful to you, but if I can help you in any other ways, please let me know. Until next time, God bless.